Okay, let's get started. Hi guys, good morning. My name is Kishore Gopalakrishna. I'm working at LinkedIn, and I've been working on projects like Espresso and Helix. For those of you who have not heard of Espresso, it's the backend distributed data store at LinkedIn that powers LinkedIn's homepage. And prior to LinkedIn, I was at Yahoo. I've been mainly focusing on the ads infrastructure team, and as part of that, I also built Apache S4. So in the next 25 minutes, I will be talking about what are the challenges that one faces if it's supposed to build an application on top of YARN. And with the help of Helix, how one can overcome those challenges. So quick intro on YARN. I think by now most of you might be familiar with YARN. But just a quick overview. Prior to YARN, MapReduce was the only framework that used to run on YARN. With YARN, it has allowed us to run multiple applications, be it nearline or even interactive or online real-time systems. So what does this really mean? It means you can have a diverse variety of applications running on Hadoop that actually share the same set of resources. This is a huge deal because it allows us efficient hardware utilization, and it also allows us to do multi-tenancy. Again, a brief overview of the YARN architecture. YARN itself has three main components. One is the resource manager, which is central to the system. The goal of resource manager, or the responsibility, is to keep track of all the nodes in the cluster, the resource usage of the YARN, of the nodes in the cluster. And for each of the node, there is another component called as a node manager, which keeps track of what are the applications that are running on this particular node. And it also communicates with the resource manager via the heartbeat mechanism periodically. With the heartbeat, it sends the node usage, the character, all the health stats of the node. The other component that is new to YARN, or in sort of what differentiates YARN or allows YARN to run multiple applications, support multiple applications, is the application master. So the responsibility of the application master is to manage the life cycle of the application. So each framework has its own application master. For example, MapReduce has its own application master. So every framework that is, or any system that is built on top of YARN needs to provide its own application master. So with that, let's actually get started. Let's see what does it take to build an application on YARN. So a very simple example, which pretty much every internet company today probably does something like this. So you have a simple MapReduce job. It generates data on HDFS, and all you need to do now is to serve that data. So in this example, I used a Redis server. You can pretty much substitute Redis server with any other server of your choice. So prior to YARN, this would have been the same, but you would have to ship the data to a serving colo. You would have to move somewhere else because you cannot run anything else apart from MapReduce on Hadoop. But now with YARN, you can actually serve the data right from HDFS. So let's look at what are the requirements. So in today's world, everything is large. So the first requirement I could think of is big data. Of course, the data is big, so that means it doesn't fit in one machine. So we have to somehow partition the data so that we can have multiple servers serving the data. We also need high availability, because if you're using this to serve your website or serve your site, uptime is really important. So high availability is another requirement. Last but not the least, you also need efficient resource utilization. So what does it take to build such a system? So once you write an application master, sort of at a very high level, these are the things that one needs to take care of. So the first is the application master should start requesting containers to the resource manager. So once it gets the containers, it needs to start them, and then it needs to assign them, ask them to do something. In this particular case, it can be serving. And it also needs to handle the failures and the workload changes that happen in the system. What does it do when a failure happens? What should happen when there is workload changes? So let's go one by one. So the first thing is the MapReduce job. Let's make it even more simpler. It already partitions the data for the server. So the MapReduce job in this particular case has already partitioned the data into 6 ways, and it has put on some location on the HDFS. And now we need some set of servers to actually take these partitions and start serving them. So now this looks simple, but the first question someone needs to ask is, where should I get my container? Where should the container be located? How do I do the distribution of partitions to these servers? So if you look at it in detail, you probably want data affinity, because you don't want the data to be moving around, or you don't want the data to be very far from the server. So you need some kind of data affinity. And when you also do the distribution of your partition, you need to make sure that the partitions are more or less evenly distributed. And you also need to make sure that the replicas probably should not be on the same machine because of fault tolerance, because if you put both of them on the same node, if your node goes down, the whole point of having a replica is defeated. So the next point is the failure handling. So what does one do when a node fails? So the very simple answer is you will get another container from YARN. You make that container start serving these partitions. But you also need to think about what happens while I'm requesting the new container from YARN. What is the time when I go, before I get the new container, what is happening to my system? Because if you look at the slide, you have P4, all the partitions that were serving on server 3, the load that was coming is now migrated to the remaining servers while we get the new server. So what you want to do when you do the assignment is you want to think that the partitions on server 3 or the load is evenly distributed among the remaining servers. You don't want that load to just transfer to one more server, because that's going to bring down the entire server. So once you get the new server, you start moving the partitions to the new server. So the other thing that you need to handle is workload changes, because this is very common. So the capacity is no longer sufficient to serve your load. So what you need to do is get more containers. And once you have more containers, you start moving the partitions from the existing containers to the new container. So the thing that you need to think about here, the challenge is, what are the partitions that you need to move? You don't want to reshuffle your data completely. Instead, you want to minimize the movement, the data movement. And the other requirement here is you need to keep monitoring the system at all times so that you decide that you need to add new containers. So last but not the least, once the servers are serving, you want the clients to actually request these servers, send request. The question the clients ask is, where should I send my request to? If I want to contact partition P1, where is this service running? So service discovery is another mechanism that you need to provide. So just to summarize, the application which looked very simple as you have the data and you just need to start serving, has now transformed into a bunch of requirements which are quite complicated. And writing such an AM is not only hard, it's actually quite error prone. There are tons of race conditions that one has to deal with. And most of the time, people don't even think about it unless the failure actually happens. So the question we asked at LinkedIn while we were building such systems is, instead of building this again and again for every system, is there something that we can build once and can use it for multiple systems? Well, luckily, we have been working on this project from almost 3 years at LinkedIn, and this is Apache Helix. So this has been running in production since 2 years, and we have been successfully been able to use it to build a variety of distributed systems, and using this as the basic framework or the building toolkit to build the distributed systems at LinkedIn. What is Helix? It's a generic cluster management framework, but the core philosophy or the idea behind Helix is to take a system and decouple the cluster management functionalities from the core functionality of the system. So just a quick look at what is Helix at LinkedIn at this point. So if you look at it, it pretty much covers the entire ecosystem. So you have the data flowing through the database, and you have the change data capture system, which propagates all the changes to the downstream consumers. And once you have the consumers are generating indexes, and you have the search system that serves the index. On the other side, you look at the ETL framework, which is taking all this data from the database, dumping it to HDFS, and you have analytics engine that provide analytics services. pretty much every component in this picture is actually powered by Helix at LinkedIn. So a quick look at the numbers. So we even tested it at scale. So we have pretty much almost more than 1,000 nodes being managed by Helix. And the way Helix is built, it's actually already a multi-tenant service. One service can actually manage all these components together. And we have a big cluster as big as 500 nodes. And all those numbers are per data center. And not only at LinkedIn, we have also been quite successful at getting adoption outside of LinkedIn. A lot of internet companies like Instagram, Box, Turn, they have started using it for their mission-critical purposes, so they have started using Helix. So let's look at the concepts of Helix and the architecture. So in order to actually make the system generic, we had to introduce some concepts. These concepts are quite simple, and once you get these concepts, it's very easy to understand how you can actually extend these concepts or use these concepts to build your own system. So the first concept that we have introduced is a resource. A resource, for example, if you're building a distributed data system, it's a database. If you're building a pub/sub system, it's probably a queue or a topic. And if you're building a search system, an index is a resource. Generally, these resources are pretty big, so you end up partitioning them so that each partition is physically located on one of the nodes. And for fault-tolerant purposes, you can also keep multiple replicas of the data or of your resource. So we have the replication, or we call them as replicas. So then our question is, once you have taken your resource and you have divided them into small chunks, how do you assign them to the containers? This is, in essence, or in short, it's actually cluster management. If you look at pretty much any problem in cluster management, you can narrow it down or express in the form of assignment problem. Because if you look at it, most of them solve it now in a static way. So the assignment is always static. But if you add this concept of dynamic assignment, it basically is cluster management. So if a node fails, all you're doing is changing the assignment of your partition. If your workload changes, you're changing the assignment. So once you have this framework that can allow you to dynamically change these assignments in your system, you pretty much have solved the generic cluster management problem. Because if you look at even the job tracker or in MapReduce, all it is doing is it has this set of mappers and reducers, and it is now assigning them to the containers to work on it. So you can pretty much model any problem in this format. So the question is, how do we do the assignment? Because there are tons of possibilities in doing the assignment. So you need to have some kind of conditions for you to come up, or rules for you to come up with a solution. So this is where we introduce the concept of state model and constraints. So the state model is pretty simple. So it's an FSM, or a finite state machine, which has states and constraints. So the use of this, it allows one to define the behavior of your system. So this is completely pluggable, so that means anyone can define their own finite state machine. So if you look at the example that we had, in order to, before start serving the data from HDFS, you go through these sequences. The server looks at the data on HDFS, loads it into its memory, and then starts serving. So the sequence of steps that happen in your application is basically depicted here. So now the question is, what are the constraints? So constraints are basically some rules or restrictions placed on the state or a transition. So if you look at it, if I want to say that I need a replication factor of 3, all you are saying is I need 3 partitions in serving state. So that's pretty much what you give as the input to the system, and Helix automatically takes care of it. Be it failure, be it workload changes, or any time, it ensures that that constraint is always satisfied. So if you look at it, these constraints can not only be placed at a partition level, but it can also be placed at a cluster level or a node or a resource level. A quick example of a cluster, let's say that you have thousands of servers in your system, and they all go down, and because of some reason, and because of a bug or some leap second or something, and you bring them up. So the first thing that's going to happen is everyone starts loading the data, and it's actually going to bring down the HDFS node itself, the complete entire system. So what you can do that is simply place a constraint at the transition level and say that I want only 100 nodes to be actually be bootstrapping. It's very simple. You just add a constraint on the transition. So that's how you start thinking about your system. Instead of trying to program this, you see, okay, with these constraints and state machines, how can I express this requirement rather than actually programming it? So now that we have looked at the concepts, let's quickly look at the architecture of Helix. So we have three main roles. One is the participant, other one is the controller, and the client. So participant is the actual servers that are actually hosting the data or doing any kind of work. And you have a controller, which is the brain behind the system, which is always monitoring all these participants, figuring out what needs to happen in the system. And once it figures out what needs to happen, it makes the participant, it calls the participant and makes it happen. And we also have the clients, which are mere spectators of the system. That's what we also call it as spectators. And they are provided with a service discovery mechanism. So if you look at the service discovery here, it's slightly more enhanced than the normal service discovery. In the sense, most service discovery provides what is running where, but Helix takes it one step further. It also gives you what is running where and what is its state. So for example, you can know that a system is actually bootstrapping so that you don't have to send the request. So we have also incorporated the state in the service discovery. So let's dive a little bit deeper into the controller and what does it make it really generic. So the controller itself is broken, has three subcomponents. One is the target provider, the provisioner, and the rebalancer. So if you look at it, you have the input. On the input side, you have the resource configuration, the constraints, and the objectives of your system. So you just simply define all these things. And once this is defined, each of the subcomponents automatically take all these inputs and emit some outputs. So for target provider, for example, its main role or responsibility is to take all this configuration, take the health of the node, and figure out, okay, how many containers do I need to run my application? So in this particular case, it might emit 3, 10, or whatever it is, but it's the one that is looking at the health of the system, and its job is, oh, I need 10 containers. If the workload changes, it says I need 15 containers. So that's basically the role of the target provider. And the provisioner role is to take this number of containers that the target provider asked for and contact YARN resource manager to actually allocate those containers and even start them up. And rebalancer is the component that looks at all the pieces of your resource. How many partitions I have, how many replicas do I have, what are the constraints that are needed to be solved, and then it does the actual assignment to the containers. Diving deep into each of this, so the target provider itself is, as I said earlier, it takes the input as resources, the existing containers, what is the state of the containers, and it also gets the constraints. So how do you want the data locality? Do you want the affinity to a particular data node? It takes all these inputs and then makes requests to the YARN resource manager to get those containers. And the nice thing about this is it has its own way of expressing the SLAs. So you can think of it, instead of one way is definitely to say that I need 10 containers, so it will always ensure that no matter what happens, you will have 10 containers. So if a container goes down, it will get a new container. But you can also slightly now think of more sophisticated ways of expressing your requirement. So for example, if you have an ETL job or some kind of task that does some transformation, instead of saying I need 10 containers, think of now saying that I need this to be completed in 5 hours. And this target provider is now responsible to figure out what is happening in the system and how long each of the tasks is taking, and it can increase the number of containers or decrease it based on the SLA that you give. So it can get more sophisticated. So we have provided Helix has 4 kinds of, sort of 3, I would say, fixed CPU and memory. And we have provided a bin packing library, which you can probably use it for your own application mechanism, for application metrics. So you can say, I need SLA latency below 10 milliseconds, or I need to always satisfy 1 million transactions per second and such. So you can even combine multiple metrics here. So the target provider outputs 2 things. One is the number of containers, and also the spec for each of the containers. And once the target provider has provided you with this information, the provisioner's job is pretty simple. It contacts the resource manager. It says, oh, I need these containers with these spec. This is the spec that I want, and please allocate me these containers. And once that containers are allocated, provisioner also ensures that it takes the code that you need, ships it to the containers, start them, and start the participants. So the last component in the controller is the rebalancer component. So the rebalancer component, as I said earlier, is basically taking taking all these containers that have been allocated and the resources and their partitions, and then coming up with the assignment. So here we have three types, or more or less two types of rebalancers. One is the auto rebalancer. So the way why we came up with these three is auto means give complete control to Helix. So Helix figures out what is running where and what should its state be in. So if you sort of give a master slave model, it completely controls, oh, this should be the master and this is where it should be running. So you give complete flexibility to Helix. Semi-auto is sort of, you give control for the state, but you take the control on where should things be running. So let's say you have a preferred set of nodes a task should be running. So you can give that as the input. You can say my resource P1 should always be located on N1, N2, N3. So it will always ensure that they are on N1, N2, N3 and doesn't change it. But it figures out what should the state of that partition be in on N1 and N2 and N3. Static is pretty much like what you have without Helix. But you can still use Helix and then just simply upload the new assignment of your system. So Helix doesn't do anything dynamically at that point, but ensures that the new assignment gets applied to the system. And user-defined is you can actually write your own user-defined rebalancers, which can be more sophisticated. So once you have, once the assignment is computed, rebalancer also looks at the current state of the system. So this assignment is what we refer to as the ideal state. So this is the state that you want the system in. And it looks at the current state of the system. It looks at the ideal state, and it sees the finite state machine, and it figures out how do I take my system from its current state to the ideal state. It applies the finite state machine transition, computes these transitions, and sends these transitions to the participant. And all these things are done so that keeping in mind that the constraint should never be violated. So let's get back to the example. Now that we have seen all the concepts and all the components with Helix, if we go back to the problem, it's pretty simple now. It's as trivial as configuring all these three subcomponents in the controller. So you configure the target provider, the provisioner, and the rebalancer. You pretty much don't have to write any of the application master code. So let's look at the configuration. So you have the app configuration, which has more or less like what is the name of your service, what are the path, where is your app data directory located, and what is your app master package. So we generally have the generic application master package which you can use, and you just provide the configuration. And configuring the provisioner is you just provide the YARN resource manager location. Where is the YARN resource manager? That's pretty much what is needed for the provisioner. And the target provider, we have taken the version of the bin packing, and then we have implemented a Redis target provider. So the goal here is it always ensure 1 million, that it can serve 1 million transactions per second. And if the system is not able to keep up with that, it automatically scales up, and it adds more containers as well. So in order for the target provider, you can also provide the range that you always need to maintain, a min and a max. So you can say I always need 10 containers, so it ensures that there is always 10 containers, but you also give it the flexibility that it can go up to 25 containers. And rebalancer is, you configure that with the partitions that are in the system. So you say there are 6 partitions and 2 replicas, And you can even place constraints like how many partitions a node can hold or a container can hold. You can say, I don't want it to hold more than 4 partitions. So all these things are taken into account when you're doing when rebalancer is computing the assignment. And the other thing is also the minimizing the movement. So when you may have more nodes in the system, when you add more containers, you want to minimize the number of data movement. That's pretty much it. So once you have that configuration, you provide this to the YARN app launcher that we have, and the entire system takes care of itself. So things can go down, the workload can change, but you see that the system is automatically recovering and maintaining your transactions per second that is needed. So the system auto scales up and down. Now let's put this together with YARN. So how does it work when you have this configuration, and how does it work with YARN? So the client simply submits, this is the YARN job launcher. So you submit the job to the resource manager. You give the configuration to this client, and the YARN launches the application master. Now without Helix, one would have to write this application master. But with Helix, all we do is start up the controller in the application master. That plays the role of a generic application master. And once this gets started, the provisioner, the target provider computes the number of nodes, and the provisioner looks at the number of nodes starts request the resource manager. And once the provisioner has requested it, it also allocates, once the allocation is done, it starts up the container. And as part of starting the container, the participant is started. So if you look at it, the participant is started empty. It doesn't have any work to do at this point. And that's when the rebalancer comes into picture. It looks at, oh, I have the containers, I have this set of partitions that needs to be assigned, and it assigns the work to these participants. So that's pretty much the entire flow, and this flow keeps repeating at any change in the system. So for example, if there is a fault, or if there are any other changes in the system, the workload changes, this loop always repeats. The target provider looks at, computes how many containers I need, the provisioner allocates or deallocates the containers and starts and stops, and the rebalancer changes the assignment. So these are some of the simulation results that we did on this. So if you look at this, so what we have done here is we have run this simulation over a period of time, and we have dynamically changing the target TPS that we want. So you can change the system from outside. You can say, I need to handle 250K. So you see that the number of containers increase, and it increases all the way to million, and then the transactions per second, and we have dropped it down gradually. So the yellow line here shows the number of instances that were needed to satisfy those transactions. So all these things are happening dynamically. So the auto scaling part can be seen here. And the next thing here is the failure handling. So what we did, we took the system, we had almost close to 32 nodes, and then we randomly inserted failures in the system. So we took like 5% of the nodes, we just took it down randomly, and 5%, 10%, and 20%. So you see that when we take down the machines, the transactions per second drop down, but they quickly recover. So how fast they recover depends on how fast YARN can actually allocate. And this was a small set of machines that we played with, and it was older version of YARN. Hopefully, we can get containers much faster with the new improvements done in YARN. So that's pretty much it. To summarize, if you are building a new application master, it's pretty hard. And what Helix has provided is a way for you to configure the system in a declarative way, rather than you trying to program for all the different possible error conditions in your system. And not only that, fault tolerance and cluster expansion and all these things are thought of as second-class citizens when you're generally developing the system the first time. But Helix automatically provides for all of these in a transparent fashion, so you can actually benefit from that. I haven't touched this point a lot, but one thing to note is this is sort of a stepping stone or a first phase in order to improve the utilization of your cluster. So YARN is provided as a way for us to run multiple containers in the node, but Helix can take it one step further. You can actually run multiple tasks within the same container and be able to use the resources within the container in a much better fashion. So once you have this task model concept, it's easy to think of coming up with sophisticated rebalancers and the target providers that allow you to take this one step further. So that's pretty much it. We are definitely looking for contributions in Helix. So we are an open community, and it's a part of Apache project. So we love helping. We are quite responsive on the email thread, and we also like to be helped. And special thanks to the Helix team at LinkedIn. Kanak and Jason have been working very hard on this. They handle all the corner cases and make sure that the system is robust, because pretty much most of the components at LinkedIn depend on Helix. And any questions, feel free to ask us at Apache Helix, or we are on the IRC as well. Thank you. I can take questions at this point. No, I couldn't get that. Can you? Okay. So you want to know what partition is located in which server? Is that supported? Oh yeah, so that's the service discovery part. So that comes by default. So you pretty much know everything in the system, what is running where and what is its state. But I need to write something, or it's already supported? It's already supported. So yeah. So you have we provide something called as a routing table. And you can just use that, and you can contact. You will know, given a partition and its state, you know what are the servers in that particular state. So that routing table is actually updated itself. Exactly. So everything is dynamically maintained. So any changes happen in the system, the routing table automatically gets refreshes behind the scenes. You don't have to worry about that. Mm-hmm.
Can I?
Good.
Okay. Hello. First, I would really appreciate the flow of your presentation.
Oh,
this is really very structured. It really helped understand, from one step to the other. But one question I have is, when you are having these container allocations, do you have any concept of, say, priority of applications or jobs, like maybe a certain kind of jobs which is already using up containers, and then that is followed by another set of jobs which deemed is more of higher priority, or maybe revenue-bearing type, which should get preference over the other? So will the containers for the previous jobs kind of get on hold, or release it for the following job, something like that? Because I wanted to get an idea of where you are focusing on the multi-tenant aspect in your topic. That I didn't find, so to say.
So two things. One, we don't try to solve the priority problem. We rely on YARN to actually give us that. So YARN already has the queue concept of queues, and you can the jobs that get into that queue, they can have the hierarchical priority there. So we rely on YARN to release that containers, or say preempt that containers, that you have to you have to stop doing that. And once we get that callback from YARN that you have to preempt, we honor that and stop the job that is happening in the system. So that's your first question. And the second question, in terms of multi-tenancy, that's the task model that I spoke about. So that's the one that will take us in the direction of multi-tenancy even within a container. And if you look at the LinkedIn architecture, all the systems, it pretty much already does that. But what it does is, it's within an application. So for example, the Espresso database that we are running is already multi-tenant, but we are not mixing different types of applications. So within an application, we know the different types and we know the workload. So we are playing it safe, but we are not mixing different types of application. So what we are doing now is combining. YARN allows us to mix different types of application, but within the container, we can actually reuse it or put multiple jobs. So for example, if you have two MapReduce jobs from the same user or the same set of folks, we can actually share the container. You can have more number of tasks running within a container than just one.
So if I understand you correctly, then for the similar kind of job types or jobs of one group, there you have this model. You're not
Correct.
mixing up with
Correct.
multiple different kind of use cases of business applications.
Not
so
at
to
this
say.
point.
At
We
this
let
time.
YARN deal with that in terms of container isolation.
Okay.
But within the same container, we can actually do more.
And on the queue side, you're saying that you let YARN drive the preemption. In that case, do you set the priority on the queues? Like, is that configured that these queues will be of higher priority?
So the YARN user set that priority on the YARN itself, and they submit it to a particular queue, and we honor that.
Okay. Okay. Thank you.
Okay, I got a question. So appreciate your talk, and it's a very good work. So can you please give me some hints? How do you compare the Helix with the Mesos or even the Omega, those similar systems?
So you said Mesos, and what is the other one?
Mesos, Helix, and Omega.
Omega?
Yeah.
Oh, I see. So I have, in terms of Mesos and Helix, I think it's similar. I would say the comparison between Mesos and YARN is more or less similar, because if you look at it, YARN is controlling just the launching and allocation and deallocation of the container. But as I walk through the talk, you see that there are a lot of things that happen after the container is started. So that's where Helix come into picture. So Helix pretty much controls your application lifecycle from the start of the container to the end. But YARN or Mesos is controlling the allocation of those containers. It's like just the start and the stop. But it's not controlling what is happening after you start the container. That's where Helix comes into picture. So I think it's more complementary, like what is YARN doing or what Mesos is doing and what Helix is doing. So they can actually blend well together. So if you look at the provisioner model that I showed, that provisioner can easily be plugged into to talk to Mesos as well to get the containers, and pretty much the entire application should work. In fact, we have one of our contributors working on integrating with Mesos as well.
Okay, so how's it? What's the fundamental difference for the Helix direct descriptive language with the Mesos allocation model?
So we haven't gone full blown on the declarative aspect. So we have just started with the FSM and the constraints. So those are the only two things that can be declarative. And most of the rebalancer are pretty much a configuration. We don't have a declarative language for configuring rebalancers or the target providers at this point. And I didn't get your last part of that question.
I mean, if you use the Mesos, we can write our own allocation model to control the resource allocation. So for Helix, we also use some language, a script to control the resource allocation. So what's the fundamental difference between?
Oh, I see. So Helix is sort of, I think I'll probably take it offline so that I can walk you through with the difference on what Mesos and Helix, how they can work together. And I think that will probably help you. But at a very high level, Helix is interacting with Mesos or YARN to actually get the containers. So Helix itself is not doing the job of managing what are the containers that needs to be allocated in the system, right? So that the usage and all those things is managed by YARN or Mesos. So you are just asking, Helix is just asking Mesos or YARN, give me these containers. And it's Mesos' job or YARN job to give us these containers. And once we get the containers, Helix starts managing them and assigning work to them and doing search. But that is not done by Mesos or YARN. Mesos or YARN doesn't worry about what happens after you get the container and start. That's pretty much up to the application, right? Okay. So that's where Helix comes into picture.
Okay, thank you.
Hey, very small question. How do I specify because it's a generic AM, how do I specify the specific application knowledge inside the AM?
So one thing that I have missed is how do you handle the transitions on the call on the application side. So the FSM that you have defined, you can pretty much write a code to handle all the transitions on the participant, and you give that jar as the input. That's the application jar and the application master jar. So those are the inputs in the configuration.
So I still have to write my own application master jar?
No, application master jar is generic. but you have to write your application jar. So for example, you would write a Redis server, and it handles the callbacks on serve, on bootstrap, and stop. So those are the callbacks on your FSM needs to be implemented by you.
So if I take, let's take an example, like if I wanted to run MR, right? MR app master to Helix, how do I do that?
So you configure your, when you submit a job, you say how many mappers you need, and you specify the location constraints that you want, so that where the mappers need to run. But let's keep it very simple. You don't care where it needs to be run. So you submit your job, and the map task on the other side, when the map container starts, it says you need to load this data file. And that's basically what kicks in the mapper task.
But you need to care about the input splits and the data locality, right?
Sorry?
And input splits and the data locality,
correct.
You need to care about it, right?
So that's the rebalancer. So we have a concept of affinity. So you can specify, you can have a, when you load it, it's pretty much, you can say, give me all the locations where this data is, and that's given as the input to the rebalancer. So you do need to write that initial thing to get the locations for each of the data splits.
So
but after that,
I still need to write my input splits, the input, everything.
Yeah, you need to do that. Helix doesn't really
And
understand.
then I can ship it with your
exactly,
jar.
yes.
I see. Okay, thanks.
Hey, thanks, this is really neat. Just probably a follow-on from the previous gentleman's question about resources and partitions. So it seems pretty obvious that that's analogous to HDFS files and splits, right? If I have a file to which I'm continuously appending, for example, a data set, right? So the number of available partitions and their locations is always in flux. Is there some sort of pluggable way to feed that information into the rebalancer every time it runs? How would
So that you can repartition your file?
Right, so say my data set is ever expanding.
Right, yes, you can do that.
Something that's consuming it.
You can. So all the partitions and replicas can change dynamically. So you can split a shard, and you can add more partitions and rebalance. You can write your own rebalancer to handle that.
Okay, so that's the answer is to plug something to
you can plug in. So all these subcomponents have very well defined interfaces, and we provide out of the box, we provide some default ones which pretty much work for 90%. But people who learn more about the system, they can go and write their own rebalancers.
Gotcha. Thank you.
Thanks, really great talk. You mentioned we can run multiple tasks in the same container. So what's the purpose of running multiple tasks in the same container?
So there are two folds. One is better resource utilization, because generally what happens is the resource request granularity is still high. So if you ask YARN, you might ask for one core, but you may not really use that core completely. There will still be a lot of things left in that but YARN thinks that you are going to use that one core. But what we can do is we can do a two-level scheduling, which is pretty much similar to what Omega does, is we can allocate more containers until you reach that capacity, more tasks to that container until you reach that capacity. So your overall throughput of your system is going to be more, because I ask for 2 GB RAM and one core, but I can actually be able to run more tasks in that container. And I can fit in more tasks until it hits that limit, and if it hits, then we can actually ask for more containers at that point. Okay, so it's a better utilization policy, and also gives rise to multi-tenancy.
So it's more fine-grained resource allocation.
Exactly, yes. Okay. That's the goal. It's a more fine-grained scheduling than coarse grain at a container level.
Okay, thanks.
So
yeah.
Sorry, thanks for the talk. So do you guys provide task level isolation in Helix?
Sorry?
Task level isolation? Like
no, not it. So that's something that we can work on, but we haven't, because what we do is we do an application level. We say that, okay, these things belong to the same type of job, so we pretty much know their behavior.
So you cannot run like multiple kinds of tasks on the same.
No, that's not, but that's the level that we want to take it to next, because we know we can measure some things at a task level, like the CPU usage and stuff like that, but the memory model is slightly difficult for us to enforce that. Okay. But we just look at it overall. So what we do is we do like a brute force. So if we see that we add a task and the CPU increases, we have this callback stop and resume. So we can stop, pause that, and resume that. So we can brute force compute what is happening with the task when we add it to the container. But that's in a very early stages at this point.
So is Helix somewhat similar to Twitter's Aurora, like Aurora scheduler on top of Mesos?
Not sure. I think Aurora still probably takes care of the stateless services. I think where Helix, Helix can definitely take care of the stateless services, but where Helix is really helpful is when you get to the stateful services, which has states that's associated
because
with
of
that.
the YARN and HDFS.
Right.
HDFS. So the third question, are you guys running any production? Like, do you guys like run Hadoop clusters with Helix or Kafka clusters with Helix?
So right now we have and all the applications using Helix are in the online infrastructure. Online. And we also have the analytics, which is offline, but it doesn't use YARN yet. So once we have YARN at LinkedIn, we are still working on getting YARN at LinkedIn. And once we have that, we have the ETL and the analytics. So both of them will migrate to use YARN on Heix-Based.
Cool. Thank you.
Sorry. Okay. Thank you.